In the last 4 days, we've used Eigenlayer to parallelize the EVM. Ethereum has become infamous for slow transaction and block times and the consistent need for L2s. Over the years, the name of the game has become speed and transaction throughput. Ethereum and L2s need to keep up. ETH parallelization has been a hot topic throughout the life cycle of the chain, from its first mention in 2017 to Vitalik's most recent talk just a week ago. But no one has successfully implemented proper parallelization. Speculative concurrency techniques, which optimistically batch transactions, end up worsening the performance of the EVM. So we've built an algorithmic solution that anyone can use, one that efficiently parallelizes transaction execution while preserving Ethereum's core principles. This is batched. Let's check out how this works. We can visualize our algorithm through our front end. Let's start the comparison between batch processing and individual processing. Our solution to the parallel transaction execution challenge focuses on intelligently batching transactions from the mempool based on independent state accesses. Our implementation uses a state access batching algorithm to figure out which transactions can be processed simultaneously. Imagine a GitHub repo where friends work on different files. Everyone can push freely without conflicts. If edits overlap, they have to wait. Our solution groups users so that they work on separate files, enabling simultaneous pushes. As we can see here, the batching algorithm is almost finished, while individual processing is no less than halfway done. From this visualization, you can see how much faster batch actually is when it comes to Ethereum transaction processing, all while maintaining the same state changes that individual processing would have. As we finish for the individual processing simulation to finish, we can actually take a look at a few calculations that we've made based on the simulation. Once it finishes, we can take a look at the average processing time after the block is finalized. Looking at a performance comparison, we can see that Eigenlayer AVS batching is around 34% faster. But why build an AVS for this?
Let's look at the actual AVS we built using Eigenlayer, deployed using Authentic, and created a blueprint using Tangle. Now on the left, you can see the Eigenlayer AVS running with its executor service, validator service, and the parallel execution helper working there, picking up transactions. On the right, I've zoomed in on the executor service, and what you can see is proof of task, which is essentially the block made up of parallel transactions and sequential transactions posted on IPFS, and the hash of that computed and submitted as data, and which is on chain. And now we're gonna take a look at what the contents of the block are. So I'm just gonna paste the IPFS hash here, and this is an actual block made out of mempool transactions, which has parallelizable batches and sequential transaction, which couldn't have been in one of these parallel batches.
As mentioned earlier, it's important to view the cons of previous concurrency attempts, namely the infamous speculative concurrency, which proposed optimistically executing transactions in parallel threads. If there are collisions between these transactions, they are discarded and rerun sequentially later. However, rerunning transactions ends up wasting time, and previous research has proven that this makes execution slower than sequential processing. Parallel execution only works efficiently when batches of parallelizable transactions are pre-decided and are valid. This underlies the importance of being correct and having somebody you can trust who can do these parallel batching for you. We have created the off-chain AVS using both Authentic and Tangle Blueprint. This AVS allows us to quickly calculate the batches to propose while also ensuring the validity of the algorithm across multiple operators. This technique wouldn't have been possible without AVS. We needed a solution that could be validated but quickly and trustfully processed with high speeds. Now let's take a look at the batched front end. Right now, the tool is suggesting 5 parallel batches of transactions. In the 6th batch, the remaining transactions are processed sequentially. Through analysis of historical Ethereum blocks, we found that parallelization on the basis of state access allows us approximately a 1.54x increase in ETH mainnet throughput. On the main page, you'll see the current proposed block, which is built by reading directly from the Ethereum mainnet mempool. We made it easy to visualize the transaction density of the batches. The deeper the purple, the more transactions in the batch. If you scroll down, you'll also find a breakdown of every transaction within each batch, complete with transaction hashes. This allows client-side users to explore and analyze individual transactions, ensuring full transparency into the batching process. The metrics that you can see on the dashboard are the current values of the fees of the transactions in the batch. The potential MEV is calculated by mean approximation, which is a further area of improvement. But what are the current incentives for proposers and sequencers? In the current state of Ethereum, we propose a basket of public goods for mainnet proposers and decentralized sequencers to adopt parallel execution. We've customized a solution where the more parallelizable the block, the higher the public goods reward. However, in the future, we aim to implement gas-based rewards for a more thorough incentive structure. We have also begun the development of an execution client using Geth to enable parallelizable transactions on the ETH mainnet. You can take a look with our code, and as a proposer, you can even use our data to propose your own blocks, giving way for usage in ETH mainnet, L2s, and even Alt L1s. You can take a look at the progress of our client development in the README of the GitHub repo, where you can also take a look at the rest of the code.